slowly. Albert Einstein was wrong. Now, that's not something you hear very often. He was right about relativity, he was right about the photoelectric effect, and he was even right about things he didn't think he was right about, like gravitational waves. But there was one thing that kept him up at night, one aspect of quantum mechanics that he simply refused to accept. He called it spooky action at a distance. He believed that the universe had to make sense, that objects had defined properties whether you were looking at them or not. For decades, this was just a philosophical debate between giants of physics. Was the universe real and local, or was it something stranger? Then, in 1964, a physicist named John Stuart Bell figured out a way to stop arguing and actually check. He turned a philosophical question into a lab experiment. Today, we are going to walk through Bell's test, the experiment that proved Einstein wrong and revealed that the universe is far weirder than we ever imagined. To understand the test, we first need to understand the argument. In 1935, Einstein, along with colleagues Podolsky and Rosen, published a paper, the EPR paper. They were bothered by entanglement. Imagine we generate two particles, let's say electrons, that are entangled. This means their properties are linked. If one spins up, the other must spin down to conserve angular momentum. But according to quantum mechanics, until you measure them, they are in a superposition. They are both up and down at the same time. Einstein hated this. He asked, if I measure my electron here on Earth and find it spin up, the other electron on Mars instantly becomes spin down. How did the Mars electron know? Did a signal travel instantly? That violates the speed of light. Einstein proposed a simpler solution, hidden variables. Think of it like a pair of gloves. If I put a left glove in a box and send it to Mars and keep the right glove here, the moment I open my box and see a right glove, I know instantly the one on Mars is left. Did I magically influence the glove on Mars? No, it was always a left glove from the start. We just didn't know until we looked. Einstein believed particles were like gloves. They carried hidden instruction sets that told them what to be. The universe is locally real. Local. Things can only influence their immediate surroundings. No faster than light spooky stuff. Real. Objects have definite properties. Gloves are gloves, even when no one is looking. It sounded perfect, common sense. But Niels Bohr and quantum mechanics said no. The gloves are neither left nor right until you open the box. For 30 years, everyone thought this was impossible to prove. How do you check if a particle had a property before you looked at it? If you look, you change it. Enter John Bell. He realized that if Einstein's gloves, hidden variables theory was true, the statistical results of many measurements would follow a certain logic. Let's simplify Bell's math using an analogy. Imagine Alice and Bob are measuring these entangled particles, but instead of just measuring up or down, they can rotate their detectors to 3 different angles, 120 degrees apart. Let's call them setting 1, setting 2, and setting 3. If the world works like Einstein thought, if the particles are like gloves with hidden instructions, they must leave the source with a plan. For example, a particle might leave with the instruction, if measured at setting 1, be up. If measured at setting 2, be up. If measured at setting 3, be down. If you run the math on all possible instruction sets, permutations, you find a strict limit on how often Alice and Bob's results should match when they choose different settings. This limit is called Bell's inequality. Basically, Bell said, if Einstein is right, the correlation between Alice and Bob cannot exceed a certain number. It's a strict mathematical ceiling. But quantum mechanics predicts that because of the wave function superposition, the correlation can break that ceiling. So the test is simple. 1. Fire millions of entangled particles. 2. Randomly change the detector settings for Alice and Bob. 3. Count the matches. 4. If If the number is low, Einstein wins. If the number is high, quantum mechanics wins, and reality is spooky. Bell published this in 1964, but it was just a theory. It took experimentalists to build the machine. In 1972, John Clauser did the first test. He taped together existing equipment using duct tape and spare parts. His results? They violated Bell's inequality. Einstein was losing. But critics argued there were loopholes. The locality loophole. Maybe the detectors were talking to each other. If they were close enough, a signal could travel between them at speed of light to coordinate the results. In the 1980s, Alain Aspect in France built a better experiment. He separated the detectors so far apart and switched their settings so fast while the particles were in flight that a signal traveling at speed of light couldn't possibly reach the other side in time. The result? Bell's inequality was violated again. Finally, Anton Zeilinger and others took it to the extreme, shooting entangled photons between islands and even using light from distant quasars to determine the settings, ensuring that nothing on Earth could have rigged the game. The result is always the same. The inequality is violated. The glove's logic fails. So, what does this actually mean for us? It means one of two things must be true, and both are mind-bending. One, locality is false. What happens here can instantly affect what happens across the universe, defying our concept of space and distance. Two, realism is false. Objects do not have defined properties until they interact with something else. The moon might really not be there in a definite state when no one is looking. Most physicists today accept that we must abandon local realism. The universe, at its fundamental level, is not made of separate, distinct objects with hidden instruction sets. It is a deeply interconnected web of probabilities. In 2022, Clauser, Aspect, and Zeilinger won the Nobel Prize in Physics for these experiments. They proved that the spooky action Einstein hated is real. It's not magic, it's the fundamental operating system of our reality. The universe is not like a pair of gloves in a box. It's more like a pair of magic dice that are blank until they hit the table, and yet somehow always land on the same number. Thanks for watching. If you want to dive deeper into the actual math of the inequality, check out the links in the description. And remember to like and subscribe for more spooky physics.